Hey everyone, welcome. Today we're going to unlock one of the most powerful and honestly one of the coolest tools in calculus, finding the exact area trapped between curves. Now this isn't just about abstract numbers, it's about measuring really complex, real-world shapes with perfect precision. Let's dive in and see how it's done.
Think about it for a second. A simple box is easy, right? It's just length times width. But what about the space between, say, a sine wave and a cosine wave? There are no straight edges anywhere. At first glance, it seems totally impossible. But by the end of this, you'll see it's not only possible, but actually surprisingly elegant.
So here's our game plan. We're going to start with the core idea behind all of this. Then we'll build our main tool, the top minus bottom method. We'll put it to the test with a real example, and then, this is the fun part, we'll throw in a clever sideways twist for trickier situations. And finally, we'll wrap it all up with the key takeaways so you don't fall into any common traps.
Okay, so how in the world do we tackle that impossible-looking curvy shape? Well, the trick is to stop thinking about the whole thing at once. Instead, we're going to break it down into incredibly simple little pieces.
And here it is. This is the big secret, not just for this, but for pretty much all of integration. We're going to fill that weird curvy area with a ton of super thin rectangles. Each one is just a basic rectangle, easy to measure. The absolute magic of calculus is that it lets us add up all of their areas, all infinitely many of them, to get the perfect exact answer. This whole slicing idea is the key.
All right, let's make this slicing idea a bit more formal. Our main approach, the one you're going to use most of the time, is what I like to call the top minus bottom method. Think of this as our go-to tool for the job.
So for any one of those tiny rectangles, how do we find its height? It's actually way simpler than it looks. At any point x along the bottom, the height of that slice is just the y value of the curve on top minus the y value of the curve on the bottom. That's it. Top minus bottom gives you the height.
Okay, we've got the height, so the area of that one little slice is just its height times its width. And in the world of calculus, we call that infinitely small width dx, which just means a tiny little change in x. So the area of one tiny slice is just top minus bottom times dx.
And boom, here's our complete tool. That big curvy s thing, that's the integral sign. All it means is sum up everything that comes after it. So we're just summing up the areas of all those tiny rectangles, starting at our point A and ending at our point B.
Now, theory is one thing, but let's actually get our hands dirty and see how this works in practice. We're going to take a real problem and walk through it step by step to see how it all comes together.
You know, you can solve pretty much every one of these problems with a simple, repeatable three-step process. This is our roadmap. First, we find out where the curves actually cross each other. Second, we figure out which one is on top. And third, we build our integral and solve it.
Okay, here's our problem. We've got two parabolas. To find out where they meet, you just set their equations equal to each other. A little bit of algebra, and you'll find they cross paths at x equals 0 and x equals 1. And just like that, we found the a and b for our integral.
All right, step 2. We need to know which curve is on top between 0 and 1. The easiest way to do that is to just pick a test number in between, like 0.5, and plug it into both equations. Whichever one spits out the bigger y value, that's your top function. In this case, it's 2x minus x squared.
Now we just build the integral. It's the integral from our start point, 0, to our end point, 1. And inside, we put our top function minus our bottom function. All of that is getting multiplied by that tiny width, dx. So we simplify what's inside the brackets to just 2x minus 2x squared. We do the integration, and then we evaluate it from 0 to 1. And the result? The exact area trapped between those two parabolas is exactly 1/3. How cool is that?
Okay, but what happens when the curves are kind of sideways, or if a function loops back on itself? Sometimes there isn't a clear top and bottom curve. For situations like that, we need to flip our perspective.
So instead of thinking in vertical slices, let's think in horizontal ones. Check out the change in thinking here. With a horizontal slice, its height is now a tiny little change in y, so we call it dy. And its width, well, now that's determined by the function on the right minus the function on the left. And this gives us our second big formula. Notice what's different. We're integrating with respect to y, so it's a dy at the end. Our limits of integration, c and d, are going to be y values. And to get a positive width for our rectangle, we always do the right function minus the left function. All right, let's put this new sideways tool to the test. The process is going to feel really familiar. We just have to remember to think horizontally instead of vertically.
Okay, this time we've got a straight line and a sideways parabola. Step 1 is the same as always. Find where they intersect. We set them equal and solve, but this time we're solving for y. Turns out they cross at y equals -1 and y equals 2. Those are our bounds.
For step 2, we're not thinking top versus bottom, we're thinking right versus left. So let's pick a test y value between our bounds, something easy like y equals 0. Plug it in. The line gives us an x value of 2, the parabola gives us an x value of 0, so the line is on the right.
Last step, set up and solve. We're integrating from -1 to 2. Inside we have our right function, which is y plus 2, minus our left function, which is y squared, all with respect to dy. Work it all out, and the final answer is 4.5, or 9/2 if you prefer. So there you have it, our two main tools for finding the area between curves. Let's wrap up with a quick field guide to help you nail this technique and, more importantly, to help you avoid the most common mistakes people make.
Okay, listen up, because these are the classic trip-ups. Number 1, always double-check you're doing top minus bottom or right minus left. If you get it backwards, you'll get a negative area. Number 2, make sure your bounds match your variable. If you have a dx, you need x bounds. If you have a dy, you need y bounds. And please, don't forget to find the intersections first. And finally, just be careful with the algebra. That's where little mistakes love to hide.
And really, this is the main takeaway. This simple idea of adding up tiny little slices lets us measure incredibly complex shapes that show up all over the real world. This isn't just some abstract classroom exercise. It's the mathematical foundation for engineering, for physics, for design. You now have the tool to calculate the cross-sectional area of an airplane wing, or the force of water pressing against a dam. So the only question left is, what are you going to build with it?